Today, I'd like to explain variance analysis in a simple way, and how it differs from conventional design and analysis methods. For example, think about the dimensions of an assembled product, or the amount of water in a tank. In conventional methods, when adding two values together, if each value has a standard deviation of, the total variation is calculated using the square root of the sum of squares. Using standard deviation assumes that all variations follow a normal distribution. For example, if anything beyond 2 is considered defective, the defect rate is expected to be about 2%. However, real manufacturing data rarely follows a perfect normal distribution. In practice, distributions are often heavily biased or spread across the full tolerance range because of manufacturing conditions. In those cases, the actual defect rate can become much higher than predicted by conventional analysis. When I worked as a designer, we did not rely only on standard deviation in software or hardware design. Instead of treating variation simply as a difference from the average or nominal value, we treated each parameter as an actual distribution with its own shape. We used kernel distributions based on real measured data, and performed calculations directly on the distributions themselves. At first, this method could only handle independent variables, but now it can also handle correlated or fully dependent distributions. By calculating the exact resulting distribution, we can evaluate probabilities much more accurately and make better engineering decisions. Here is a simple comparison between conventional numerical analysis and distribution-based analysis for handling variation. Standard deviation, which is widely used in conventional calculations, assumes that all variation follows a normal distribution. As I mentioned earlier, real manufacturing data often does not follow this pattern, so important trends in the actual data are lost, creating errors in the analysis. Another common method is the Monte Carlo simulation. This method repeatedly changes parameters randomly and calculates the resulting distribution. If there is only one source of variation, Monte Carlo methods can produce reasonable results. However, when multiple variation factors are combined, errors remain in the resulting distribution no matter how many simulations are repeated. This means the probability accuracy is often insufficient. I explained this in another presentation. This also suggests that even large-scale data, such as big data, can still contain hidden errors when multiple variation factors are mixed together. Distribution-based analysis solves this problem by directly calculating the full distribution of models that include multiple variation factors. This makes it possible to calculate probabilities accurately and improve confidence in performance and reliability. To make correct engineering decisions with high accuracy, we need three things. Understand the distribution of each individual variation factor. Obtain results using distribution operations, which extend the scope of operations from numerical values to distributions. Use probability-based evaluation indices based on the resulting distributions. I believe this approach should become an essential part of design and analysis in every engineering field.